In recent years, there's been a lot of talk about Class D amplifiers, but how do they differ from the predecessors like Class A and Class AB? Today, we'll discuss that topic. So the Class D amplifier, what is it? And what makes it so advantageous to use? Or why has there been an upsurge in Class D topology in the audio world? Now keep in mind the Class D has actually been around for a while. It just hasn't been refined as much. It has been used extensively in bass amplifiers for bass instrumentalists in the live music world. And it's also been used extensively in live audio, right, for concerts and things of that nature. To push speakers at wattages upwards of 500 to 1,000 watts. But before we talk about the topology and how the Class D amplifier works, let's first cover its predecessors, the Class A and Class AB. So how does a Class AB amplifier work? And what makes it so different than a Class A? Or a Class D, excuse me. A Class A and a Class AB, for that matter, are very linear amplifiers. So a Class A and a Class AB work generally like you would think of a basic amplifier, in that it has a small signal input, and that small signal input gets translated into a large signal input, which would be a sine wave in this case, right? So a typical, let's say, I'm going to go in between using vacuum tube topology and transistor topology here. So let's say a typical vacuum tube Class A amplifier will look something like this. I'm going to bypass the components here, but just to get a basic idea. So this would be our driver for the gain that would drive an output tube. Let's say it was an output pentode, like your 6L6 GC or your EL34. It would have a gain stage to drive it, going into the grid, going to the plate, and this plate would be hooked up to a transformer. There would be B+ here, high voltage here. This would be biased such that this tube would be operating like near 90%. And this would be your speaker out. Now, that's the basic topology of a Class A amplifier, of a vacuum tube Class A amplifier. Now, why wouldn't you want to do that all the time? Well, especially when it comes down in transistors. In the transistor world, it comes down to efficiency. So doing this, and in the vacuum tube world, the same thing kind of remains. Whereas doing this, the sound of a Class A amplifier is actually oftentimes very much preferred. This is why there's also an upsurge in Class A monoblocks, for instance, in the vacuum tube world. Though they can be a bit inefficient. Why? Because the tubes run very hot and they're running all the time. And that's the basis of a Class A amplifier. So if I was going to define just simply what a Class A amplifier would be, it would be an amplifier that's running, let's say, near 100%. So Class A would equal an amp running near 100% all the time. That means that the amplifier is running all the time, whether or not there is any signal being applied at the input. And even in the event that there's any signal there, how small or large, doesn't matter. This thing is always conducting almost near 100%. So there's a lot of wasted energy because of that, which makes it inefficient. This, though, isn't so much of a problem when it comes to tubes, though it will wear out your tube life. Right? So if you do something like Class AB, which is oftentimes called push-pull, which we'll look at later, that gives you the ability to split the workload between two tubes rather than it being centered around this one tube. Therein, your tube life is preserved. But Class A, again, doesn't have as many limitations in the vacuum tube world as it does in the solid state world. One of the other limitations that you could find in the tube world for a Class A amplifier is that you're limited with wattage to a certain degree, and it becomes even more inefficient as you're trying to get any wattages, let's say above 20 watts, 30 watts. You could push something like a KT88 maybe to 30 watts using one tube, or else you'll parallel the tubes. And this is where it gets inefficient in the vacuum tube world, is that, let's say if I want to make a 60 watt amp and I can get 30 watts out of a KT88, but I want to make a 60 watt Class A monoblock. Well, what I'm going to have to do is parallel this tube with another. Right? Do something like that, and then just parallel these tubes together, and that's how you would get your 60 watts. But again, that makes it more inefficient. The most efficient way to do that would be to go Class AB, which is what we're going to talk about next, which is basically a push-pull topology, where you would have one tube doing half of the cycle and the other tube doing the next cycle. Because putting them in parallel like this works, but again, then they're always working at near 100%, and you're going to degrade the tube life. So there's still a lot of wasted energy. But in the transistor world, again, this is even worse, because if we remember back, tubes operate on high voltage, but solid state devices run on current, especially power amps. They need high current. So for a transistor, let's just do another block diagram, or a little sketch of a transistor amp here. You would have your gain stage driving your output. Now keep in mind that, especially for a transistor, it's very uncommon that there'll be just one transistor for the output stage. This is another reason why it's actually not that inefficient or unfeasible for this kind of topology to take place on in a vacuum tube amplifier, because one vacuum tube can actually produce a good amount of power even though you're running it very high. Whereas typically your average transistor isn't going to be able to produce that much wattage on its own, so it's going to have to be paralleled with other transistors. But for the sake of this example, we'll just leave it like this and say there's only one transistor here. So this would be our power transistor. There would be a capacitor here, and that would be our output. So This would be your Class A amplifier for a transistor amp. Now you have to say, okay, well, what's so inefficient about this? Well, unlike vacuum tubes, which actually enjoy a bit of heat, right, because they are thermionic valves, right? So they're thermionic devices that actually need heat to operate, though excessive heat can degrade them. Transistors, on the other hand, do not need heat to operate, but actually derive heat from being inefficient. So the hotter a transistor runs, typically the less efficient that topology is. So what happens here with the Class AB amplifier in the transistor world is that it needs a lot of high current. So that means you have to have what? A big power transformer, right? So you have a big power transformer, which is also very heavy and expensive. Then you have all that energy going into a transistor or a couple parallel transistors that's now taking that energy and wasting it in the heat sinks. Right? So all that energy that's being consumed by this transistor, a great portion of that is going and being dissipated as heat. So this is one reason why it's very inefficient to run transistors in this manner. Even though, just as in the vacuum tube world, there are solid state listeners and solid state designers that prefer the Class A operation, again, mostly for its linearity, because as we can see from just a block diagram here, it's very linear. So that you have your sine wave, which was your input, comes here, it grows a little bit bigger here, and then it gets even bigger here, right? So it's just a basic kind of linear way to step up the voltage swing of an amplification device. Thereby, it keeps the signal path as true as possible. And that's what we're always looking for in audio, is trying to reproduce the signal at a higher voltage, higher current, higher wattage, but wanting to preserve the signal's characteristics. So we don't want to modify it very much at all, right? So this, doing a Class A, helps us with linearity. It helps us preserve that input signal, which is the recording that comes from an MP3 or a CD, and preserves that signal as cleanly as possible throughout the amplification process. So again, why don't we want this in a transistor setup and a transistor topology? Because of weight and heat dissipation. It becomes highly inefficient because of those two things. Okay? Now, and I think I'll start with vacuum tubes again here, but the principle remains the same for transistors. And if we're going to move to Class AB, what do we have? Well, we have what's called a push-pull topology, which is where you'd have your pentode. You'd have two pentodes now working together. Looking something like this. And these two pentodes are going to be tied to an output transformer. Let me get down here, this will be easier. This pentode will be tied to an output transformer. Okay. And whatever your impedance here for the speaker, let's say it was 8 ohms, would be there. But now, of course, to drive these pentodes, what do we need? Well, we need two signal sources. So what's going to happen here is a push-pull or Class AB amplifier is going to be driven by what's called a phase splitter. So it'll have your signal coming in from your preamp, or it could just even be a whatever the signal source is. It's going to come in here, and that'll come through the first gain stage. But in this case, it'll be a phase splitter. And all that means is that instead of like a typical gain stage where we'd come out of the plate, here what we're going to do is we're going to come out of the plate, which of course is going to be inverted. So we're going to have the same signal, but upside down, basically, right? So we're going to have this signal, and that signal is going to come up here. And then we're also now going to take a signal from the cathode. So we're going to get two signals out of this, out of that phase splitter, right? So we're going to take the inverted and the non-inverted out of here. And of course, in a scenario like this, we'd want them to both be the same voltage, right? So we want to get those signals as close as possible. So one tube is going to get the inverted, and one tube is going to get the non-inverted. Now this is a basic topology for a Class AB pull-push amplifier. Now why we call this pull-push? Well, because one pentode will take up the positive cycle, and then one pentode will pull on the negative cycle. So the positive cycle will push the speaker, essentially, and the negative cycle will pull the speaker back, right? So there's kind of a dynamic motion going on here. So because of this, the workload can be split. So in a Class AB, the amp will be running 50 to maybe even 70%, which would be on the higher side. But because of that, then you're able to get more wattage per tube, and you're also able to run them a little bit cooler, right? So that will help in your tube life as well. So these things are not going to be on all the time. They're going to be on 50 to 70% of the cycle, right? So depending on how you bias this, now that's another topic, but it depends how you bias it. And typically, when manufacturers want to be more specific about how the bias is going to, and what the duty cycle is going to be, and what class they want to run it, because there's also a Class AB1 and AB2. What we're talking about here is basically AB1, but there's a Class AB2 as well. Now that is represented by how much bias voltage you would have here. Now, typically on a vacuum tube setup, the easiest way to dictate how much or what the bias point is going to be is to inject a negative voltage here at the grids and have a negative volt supply to dictate how much these tubes conduct. And that negative voltage supply will dictate if you're running Class A or Class AB. Just for an aside, you can get actually more wattage out of Class AB2. So for instance, I believe if you have two pairs of EL34s in Class AB2, they could run about 75 watts. Whereas, let's say, if I just had one EL34 at Class A, I might be running 15 to 20, right? So you can see the disparity there. So it becomes much more efficient to use a Class AB pull-push topology when you're wanting to get more wattage. It's much more efficient. You get more out of your tubes, and they run cooler. They'll last longer. There is a bit of a problem here with what's called crossover distortion. Now we say, okay, well, what's crossover distortion? Well, crossover distortion is something that will look like this. Let me see if I can get this here on this side. So we have our sine wave, which looks like that. But because there's some modulation here between this tube taking a part of the cycle and this tube taking a part of the cycle, sometimes, especially depending on the quality of your output transformer, there's what we call crossover distortion, which means that there's a bit of distortion that can happen in the transition of the cycle. So if you look up crossover distortion, you'll see an image that looks similar to this. And the distortion would be right here. The distortion would be where the sine wave is transitioning from positive to negative, which would be right there. As you can see right here, there's kind of dips and it's kind of uneven. That's where your crossover distortion would occur. So that's something to pay attention to in a Class AB design. But other than that, they're fairly efficient, and that's actually what has dominated not only the vacuum tube high-end audio realm, but also the transistor high-end audio realm, and just basic amplification in general if you're talking about instrument amplifiers or anything else. That's been the way of the world when it comes to amplification. Let's say for the past, I don't know, it could be 50 years now. But now we have this thing coming, getting more popular, called Class D. Now, what's Class D? Well, Class D runs on a completely different type of topology that's not as linear, but the advantages are that it doesn't produce really almost no heat, so there's no necessity for a heat sink, and it doesn't consume as much power because it doesn't waste as much power as a Class A or AB would. So your Class D, which is pretty much used just in the realm of semiconductors. I'm not aware that anybody has stepped into trying to make one for a tube amplifier. It's probably just impractical at that point, and I'll show you why here. Because again, this is about conserving heat and making things smaller and making it consume less power. So a Class D amplifier works a bit differently, and it doesn't work as linearly as a Class A amplifier, Class AB, and that's because it works with something called pulse width modulation. Now, pulse width modulation is basically a process in which your sine wave becomes a square wave and then gets turned back into a sine wave at the output. So, the topology for a Class D amplifier, which is also sometimes called a switching amplifier, and we'll see why here in a second, will look something like this. So what's happening here is we're going to have something called a comparator. Now, a comparator is going to be fed the signal, your input signal, and a triangle wave, maybe even a square wave. And that comparator is basically going to combine the two signals, giving an output of a square wave. Now, this is going to be happening very quick. Let's say upwards of 100 kilohertz. And these, which are MOSFET transistors, are going to be acting as switches. And here, what we're going to have are filters. Now, this is one of the disadvantages of your Class D setup. So it works very similar to a switch mode power supply. So what's happening here is you're combining your analog signal with a high frequency triangle signal or a high frequency square wave, and you're coming out with a square wave, and your input signal is going to pulse modulate that square wave at very high frequencies, which is going to be switched on and off by these transistors. Now, if you look here, I have an example of how this pulse width modulation works. So what I have here is my function generator going into my oscilloscope, and I have a sine wave coming in, which would replicate our input signal, which is very small, which then gets turned into this square wave with the input signal injected into it. And as you can see, the width of the square wave is pulsating, and it's getting smaller and larger, depending on the amount of input signal. The wider it gets, the louder it gets, meaning the larger the sine wave is. The smaller it gets, the quieter it gets. That's where you get your amplification factor in a pulse width modulated Class D amplifier. Now, one of the major problems with this, disadvantages, is that Class D amplifiers, because they operate at high frequencies, have to be filtered extensively to get rid of those high frequencies, so you come out with just your plain sine wave at the end. So there needs to be typically an inductor there with a low pass filter, which would be there, and you'd also need a high pass to get rid of some DC voltage that would be there. So this would be L. I know that looks like that's a terrible rendition of a inductor, but that would be your inductor here. That would be L. This would be C. This is capacitor, and your capacitor, that would be a low pass, and this would be a high pass. But this is really just there to get rid of some DC voltage there. So as we can see, there are some advantages and disadvantages. One being a particular disadvantage to the topology of a Class D amplifier is that there is inherent distortion characteristics when you're translating the square wave into a sine wave. And this is why it hadn't been favored in past years, though this is also why it is favored now, is because there's been great innovation in the field of audio electronics, such that manufacturers, designers, engineers, audio companies are making Class D amplifiers with much lower distortion characteristics, while also being able to enjoy the fact that they don't exhaust as much heat, they don't exhaust as much power, Therefore, you don't have to have as big of a power transformer, as big of a power supply to run them, which makes them lower cost, it makes them lighter, and it makes them able to run at much lower temperatures, which all in all will make the unit smaller as well. So they have gained a lot of traction in the high-end field and otherwise. So that is how a Class D amplifier operates. I hope you enjoyed. Thanks for watching.